Hello and welcome back to Workbench Wednesdays. Microcontrollers have always been my favorite digital device, while operational amplifiers, or op-amps, are definitely my analog favorite. So, wouldn't it be great if some magical device incorporated both, like this one? This microcontroller is the Microchip ATmega 128DB and has actual op-amps that are configurable in software. For example, here the code is cycling through different gain stages. Isn't that cool? Well, I think so. So in this video, I show you a fun and practical way to work with op-amps without using an op-amp. Well, a discrete op-amp. All right, grab an oscilloscope and let's go measure. Before I get to the 128, I am making an assumption that you know a little bit about op-amps. If not, that's okay because Karen has you covered with an excellent tutorial on her show, The Learning Circuit. Check the description for a link to that. For this video, you can just watch, or if you'd like to follow along at home, you'll need an ATmega 128DB microcontroller, a USB to serial adapter, and a Nano to act as the programmer. You also need DX Core. It's an open source package to enable support for this chip in the Arduino IDE. And it comes with a library to make working with the built-in op-amps super easy. Okay, maybe not super easy, but definitely easier. Links to the hardware and software are also in the description below, which takes you over to the Element 14 community. Now that I've covered the basic setup, I'm going to show you a couple of different circuits that we can configure with these op-amps, starting with a voltage follower or buffer circuit. As the schematic shows, we would put a signal into the non-inverting input and connect the output directly into the inverting input. In code, we make the same connections. First, we tell the 128P to connect the non-inverting input to the physical pin on the microcontroller. Then we tell it to connect the inverting input to the op-amp's output. While that code uploads, let's move over to the oscilloscope. The scope has a built-in function generator and I have it generating a 1 kHz sine wave. That goes into channel 1 and into our microcontroller's op-amp input. A probe on channel 2 connects to the output. As I change the input signal's voltage, the output follows it. Now, let's go amplify the signal. We need to replace the short between the input and output with potentiometer, which these chips have built-in pots. To enable them, we will need to add a few lines of code. But first, we connect the inverting input to the wiper, just like in the schematic. Then we use 3 lines of code to configure the divider. The top connects to the op-amp's output, the bottom connects to ground, and we set the position of the wiper on the digital pot, which in this case will be in the middle. For the moment, don't worry about the actual wiper setting variable. You can get this code plus the KiCad schematics in that Element 14 link that I mentioned earlier. They have all of the details that I'm glossing over. Remember, with a non-inverting amplifier, the gain is 1 plus the ratio of the resistors. So in this case, the gain is 2. Which the scope is showing us. No hardware changed. I didn't move any of the connections. The only difference is a few lines of code. 2 things to keep in mind. First, the code only configures the op-amps. They operate independently of the rest of the microcontroller, which we'll see in an example at the end. And second, that wiper variable only has like 8 positions. So one potential limitation are the amount of gain settings. Well, of course, unless you use external resistors. Next, let's make an inverting amplifier. Let's take a look at an inverting amplifier with a gain of -1. Wait, is that a double negative? Anyway, it is like a circuit you would build back in school with a UA741 and a bench power supply. For the code, we connect the non-inverting input to ground and the inverting input to the wiper of the digital pot. Instead of it being connected to ground, the pot connects to the physical pin where we put our signal in. And then we connect the wiper to the middle like we did before. Yellow is still the input and blue is still the output, but that's not what we expected to see, is it? Or at least what I expected to see. Haha, I tricked you. Well, unless I didn't. These op-amps are only single supply, so they aren't like a 741 with dual supplies. Like any single supply op-amp, you need to bias the input, which we can do with a voltage divider. And the helpful 128DB already has one built in for VDD. We just need to connect it. On the function generator output, we also need to bias the signal to get the output we would expect to see. Now, I do hear some of you asking, what about that bias we just applied? The waveforms didn't move. Yeah, about that. To make it easier to see the signals on the scope, I AC coupled the inputs to remove the DC bias we added. Also, my power supply is kind of noisy, and so for some of the measurements, I had to turn on waveform averaging to clean up the display. It turns out these op amps are just as sensitive to noise as discrete op amps. Now, before we wrap up, I want to show you one cool example that helps demonstrate two ways that you could use these built-in op amps. DACs usually need a buffer, and analog signals need to be scaled for an ADC. Here's a contrived but actually practical example. The 128 dB has a built-in digital to analog converter. So we will create a waveform using some millis or micros magic and analog write. Let's pretend its maximum output is limited to 1 volt, which we can verify on the scope. The first internal op amp buffers the DAC's signal. Then its output is linked to the input of the second op amp, which is set for a gain of 4. We do that by using the Wiper 5 setting. Now, we could look at the output on an oscilloscope, or we could connect the second op amp's output to the microcontroller's digital to analog converter. Internally, the outputs are already connected to the ADC inputs. Using analog read, the chip samples the waveform from each op amp and then outputs their values over serial. The Arduino IDE has a built-in feature called Serial Plotter. And as that super clever name implies, it plots the data it gets over serial. So we end up with something that looks like an oscilloscope display. The blue waveform is the buffer DAC, and the red is the amplified signal. Just to verify, here are the same signals on a scope. And using its measurement, we can see it has a gain of about 4, just as we expected. Just to recap, we generated an analog waveform, buffered it, amplified it, and then resampled it all inside of this digital microcontroller. In the real world, you might use op amps to buffer a DAC or scale an ADC voltage, just like we did here. Pretty cool, right? As you can probably tell, I really like this microcontroller. It also has a bunch of other cool stuff that it does, I just don't have time to cover them in this video. So, over on the Element 14 community, I have a short post with some of the other things that I like about it. And this is the part where I remind you that that is the best place to ask me questions. I look forward to seeing you over there or in the next video. For now, it is time for me to get back to integrating unity gain with a properly biased cascaded operational amplifier stage with a single chip on my electronics workbench.